All right, so we have finished Newton's first and second laws. Now we're going to discuss Newton's third law of motion. Okay, Newton's third law of motion states that for every action force, there is always an equal and opposite reaction. Okay, so force cannot exist one way. Okay, if an object 1 has a force on the object 2, at the same time, simultaneously, object 2 is going to have a force on object 1 with the same object, with the same magnitude, but in opposite direction. Okay? And if you think about it, it is true in our life. If you pull something, you also feel being pulled by the other thing. Right? If you push something, you also feel a force, okay, from the thing being pushed on yourself. Okay, so you can't find any exception where when force or the force exists from 1 on 2, but there's no reaction, the object 2 doesn't have a force on object 1. So that's a law, right? If this is truth, is always true, cannot be overturned anywhere in this universe, then we call it a fundamental law. Okay, so that's a lot of people call action-reaction. Okay, action-reaction law. Okay, so if you put it in equation form, again, I would write it this way. Right, the force from 1 on 2 is always going to be the opposite of the force from 2 on 1. Okay. So, and then let's take a look at some real-life examples. Okay, take a look at the examples on the second slide. So this is a PowerPoint 6. When you use a hammer to hit the nail into the wall, okay, of course the hammer is going to have a force on the nail, right? That's why the nail goes into the wall. At the same time, simultaneously, the nail is going to have a force on the hammer, opposite and equal. Okay. Think about Earth, okay, and anything on the surface of the Earth, okay. If anything feels a gravitational pull downward, okay, from the Earth. At the same time, it's also applying a force on the Earth, okay, upward, okay, pulling force upward on this Earth, okay. And then the forces between the Earth and the Moon, okay, we know that the Earth attracts the Moon, okay. At the same time, the Moon also attracts the Earth. Okay, so everything is consistent. Okay, for every pair of force, okay, you always find them equal and opposite. Okay, between two objects. So forces are always mutual. Okay, they don't exist one way. Okay, they're always mutual. Okay. Okay, some people may have some confusions on Newton's third law. Okay, so take a look at that question on slide 3. Okay. So this is the question people usually ask when they study Newton's third law the first time. Say there are two objects like the ball and the earth, okay? They are going to exert equal and opposite forces on each other, okay? I take that. But how come when I drop a ball, right? When I drop a ball, I always see the ball falling down due to the force of gravity from the earth on the ball, but I never see the earth moving up. Okay, if you tell me there's a force from the ball on the earth, okay, at the same time simultaneously equal and opposite, so the earth should feel a force up, right? But how come I never see the earth coming toward the ball? I only see the ball coming toward the earth. Okay, how do we answer that question? Okay, the answer is this. Okay. The answer is this. First, think about it. And see if you can think it through. The answer is this. These two forces are equal, for sure. But the resulting accelerations are not. Okay? So that's a perfect example that equal causes can produce very unequal effects. Okay? They have the same cause, okay? But then the effects are totally different. We can do some math, right? We can do some math. If you say the earth, there's a ball falling, right? The ball has a force the Earth has a force gravitational pull on this ball, which is m times g. At the same time, the Earth is going to feel this force up with the same magnitude and opposite direction, right? So now we can calculate the effect, okay, of that force on the ball and the Earth, right? What is the effect of this force on the ball? Well, it's going to pull the ball down. Then what is the resulting acceleration of this ball? We know that that's going to be the free fall acceleration, right? If you drop anything, okay, and it's going to move under the gravity from the Earth on it, the acceleration is going to be little g. That's actually how we found this equation for the gravity, right? So for the ball, the acceleration is going to be 9.8 down. Okay, so that's why it's very easy for us to see that, to observe that, right? If I drop anything, I see it's moving down, so I see the effect of the force on it, okay? So that convinced me that there is a force from the Earth on the ball pulling it down. At the same time, the ball has a force on the Earth with the same value, okay? What is the resulting acceleration of the Earth? What is the effect of that force on the Earth? You're going to calculate the acceleration of the Earth, right? So you're going to do the force of gravity divided by the mass of the Earth. The mass of the Earth, okay? So what is the gravity of the ball? Okay, say the ball is 5 kilograms, just a few kilograms, right? You plug numbers in, what do you get? You get 5 kilograms times 9.8. That's the force between them, right? Equal and opposite. The ball feels the force. The Earth feels that force up, okay? But now you're going to divide it by the mass of the Earth. And the mass of the Earth, wow, that's going to be a huge number. Okay? I don't even need to put these numbers in my calculator. This is going to be a very, very small number. I don't even need to worry about it, right? This is almost going to be 0. So there is a force on the Earth at the same time, but the effect, okay, is totally negligible. You don't really see any effect because the resulting acceleration is going to be 0, almost 0, right? So the force does exist, but it's just that we don't see the effect on the Earth because the Earth has a very, very huge mass. In order to move the Earth, okay, you're going to apply a huge force on it. This force, 50 newtons, about 50 newtons is not going to move the Earth. If you apply 50 newtons on the Earth, you're not going to see any difference, right? You're not going to see any effect, okay? So that's how we answer this question. When I see two objects, okay, if you tell me there's always equal and opposite forces between them, but how come sometimes I only see one object move, the other object doesn't move, or I see the motion of these two objects are different because the effects are different, right? They have the same force on each other, but they may have different masses. And if they have the mass really different from each other, the motion you see, okay, of these two guys are going to be totally different, okay? All right? So that's how we answer that question. So I hope that clears up that confusion, okay? Now, what about the next question I want to ask you? So this is also a question people usually ask, okay? Sometimes even after they have learned Newton's third law for a long time, they still confuse themselves in this case. Think about this, okay? I'm giving you a very simple example. Say you have blocks A and B on a very smooth surface, frictionless, no friction, almost 0. And you're pushing the whole system to the right using your hand, okay? So take a look at the interactions between A and B. Of course, A is going to push B to the right, right? So B feels the force from A in that direction. So if this is B, I'm going to draw the force from A on B. Okay, so that is the reason I see B moves to the right, right? But what about A? If you draw, okay, at the same time, I'm going to isolate A. And then Newton's third law, if Newton's third law is true, the force, there is also a force from B on A, equal and opposite, right? So if this is 10 newtons, this must be 10 newtons. If that's 15 newtons, this is going to be 15 newtons opposite. But how come I don't see A moves to this direction, right? If A pushes B in that direction, B pushes A back. But if you do this, right, you can do this experiment, right? On any surface, you're pushing two things together. There's a force between them pushing on each other in opposite direction. But I always see these two guys moving together in that direction. How come A doesn't move under this force in the opposite direction? Okay, so how do you answer that question, right? If you tell me B pushes A in this direction, how come A is not moving in that direction? A still moves in that direction, okay? Is there some sort of a contradiction here? No, there's no contradiction, because if you want to figure out how B moves, you're going to draw all the forces on B. If you want to figure out how A moves, you're going to do the same thing. You're going to draw all the forces on A. So let's first draw all the forces on B. Okay, see why it moves to the right. So if I draw all the forces on B, this is what I'm going to do. The gravity of B, right? So that's going to be this. And then there's a normal force from the surface on B, right? And these two forces, okay, we know that they're going to cancel exactly. This is intuitive to everyone. So y direction, there's no force at all. There's no net force at all, right? So that's why the B is not moving. It's not even moving, right? In x direction, there is a net force in x direction. So the B is going to have an acceleration, okay, which is going to be equal to the net force in x direction divided by the mass in x direction, the mass of B, which is just going to be the force from A on B divided by the mass of B. And of course, it's going to be to the right, right? Because this force is to the right, so the acceleration of B is going to be to the right. So in this case, B is going to be moving to the right. Agrees with our experience. If you do the experiment on the surface, B will move to the right. What about A? How does A move? Okay. Now you can't just look at that force. Okay. So that's something people usually don't realize. Now let's draw all the forces on A. Gravity on it. There's normal force on it. Okay, I know these two forces are going to cancel. Okay, that's intuitive to me because A is not moving in this direction. The surface is supporting A. Now you tell me B has a force on A in the opposite direction. Okay, I'm going to take that. Is there any other force on A in this case? Of course, because you are pushing. There's a force from your hand on this object, right? And if you want to push them together to the right, you're going to apply a fairly large force to push them, right? If they're heavy. So in this case, what will be the direction and magnitude of the acceleration of A, right? You're going to do this. It's going to be net force in x direction divided by mass. And in this case, you see these two guys are going to be opposite. So you have to subtract them. And then in order to make A move to the right, you're going to make sure you apply a fairly large force so that it's going to overcome the force from B on A. So A is you still get a positive number to the right. Okay, when you subtract the force from B on A from the force from the hand, you still get an acceleration to the right because you need to take into account all the forces in x direction in order to figure out the motion of A. You can't just say, oh, there's a force on A to the left. How come it doesn't move to the left? Well, you need to tell me if there's any other force on A in other direction, right? For example, take a look at these two forces, right? If someone asks you, gravity is down on this A, how come this A block is not moving down? You would say, hey, because there's a normal force, cancels the gravity, right? You cannot just take a look at this gravity and then say, okay, my conclusion is that there's a force down on it, it must move down. If it doesn't move down, there's some contradiction here, there's something wrong here. No, because you need to consider all the forces, right? B has a force on A, pushes it back. That's what Newton's third law tells us. Nothing wrong about it, but there's another force in the opposite direction which comes from the hand, right? You imagine if you don't apply a force to this system, they're not going to move to the right together, right? You have to apply a force on this system in order to push them both to the right. So this force must overcome the force from B on A, okay? So that the net force on A is going to still be in the x direction. So both of them are going to be moving in the same direction, okay? That's how we clarify that, okay? That's how we clarify that, okay? Okay, so you can take a look at the cases on slide 7. So I want you to also think about it, okay? How do I explain that? Take a look at the first case, okay? If I hit the nail using a hammer, the nail goes into the wall because the hammer had a force on the nail in that direction. Okay? No question. Everyone's going to agree with that. But if you take a look at the hammer, then the nail has a force on the hammer. Okay? Then you would say, how come I don't see the hammer goes in this direction? If you tell me Newton's third law says at the same time the nail is going to have a force on the hammer in the opposite direction. Again, you're making a mistake. You can't just take a look at one force on this hammer and say it must be moving in that direction, right? The hammer has a force of gravity down. How come it's not moving down, right? Because you need to take into account all the forces on this object so that you can decide its motion. Is there any other force on this hammer in this direction? Of course, because you are hitting the hammer using your hand, right? You can't forget about that force. That force is from your hand. So again, you see that you have to hit the nail very hard. So actually you're not hitting the nail directly using your hand, right? You're applying a force on the hammer in that direction really large. And then now you compound these two forces, you're going to apply a very large force on the hammer. So this force minus the force from the nail on the hammer, so the net force on the hammer in x direction still going to be in the right direction. So the acceleration of this guy is still going to be in that direction. If the acceleration is in that direction, it's moving in that direction. It's pretty much like this case, right? You can't just take a look at this force on A as a reaction from the force from A to B, okay, and say, how come A is not moving that direction? You can't ignore other forces on it. You have to take into account all the forces on it so you can decide the motion, okay? You always need to consider all the forces, okay? Now take a look at the second case. So this is another case which can be confusing to people, which can have some, people can have some misconceptions on, okay? Let's take a look at this problem. Say if you are pushing a very heavy box on the floor, okay? Of course, you're going to apply a very large force to push in that way. So now let's take a look at the forces between them. So you would say there is a force from the person, right, from myself, on the box. That's why the box moves in that direction. Okay? So this is the person on the box. But okay, if Newton's third law is true, let's draw the force on the person, okay? So, okay, I can draw it here. The box has a force on the person at the same time and the opposite direction. Now, a lot of people will ask this question. How come that the person is not moving in the opposite direction, right? If the person pushes the box in that direction, the box is going to push the person in the opposite direction. How come the person is not moving in that direction? What is our explanation? What is your explanation? Think about it, okay? A lot of people, okay, I've realized that a lot of people, they would say this. Because the force from the person on the box is greater than the force from the box on the person. That's why I'm moving with the box together in that direction, okay? That's a lot of people say. The person had the force, so I push the box harder, then it pushes back on me. A lot of people would say this. I need to push the box harder, then it pushes back on me. This is wrong. This is wrong. This is incorrect. Okay, this is a misconception. Why? First of all, these two forces, they are action and reaction, right? There's a force from object 1 on object 2. There's a force from object 2 on object 1. They should always be equal in object. That's Newton's laws. This is definitely wrong, okay? You don't even need to compare them. They are always equal, always. Okay, so don't ever say that. That is actually wrong. This is totally wrong, okay? Okay, especially don't tell kids about this statement, okay? That's how a lot of people got this misconception, okay? People, because they were told that I need to push this box harder, then the box pushes back on me. No, that is wrong. These two forces, action and reaction, they are always equal in object, okay? You don't even need to compare them. They are always equal. Okay? Then, how come, what is the reason the person also goes in that direction? Okay? If there's a force from the box on me pushing me back in this direction, how come I'm still moving with the box? Again, have you considered all the forces on the person? Have you considered all the forces so you can say that you can decide the motion, the direction of the movement of this person? Let's draw all the forces on the person. So gravity is on the person, so I can draw this, that's gravity. And of course, there's a normal force on the person from the floor. So these two forces, they're going to cancel out exactly, right? Okay? So is there any force on the person in the horizontal direction? Okay? Think about it. Think about it. When you're pushing a box really hard, right? Your feet are on the floor. Your feet are pushing the floor in that direction, right? Think about it. You can do the experiment, right? When you push the floor in that direction, you are going to get a reaction force in this direction. Okay? So that's still action-reaction. So when you're doing this, you are getting a friction force from the floor in this direction because you're pushing the floor in that direction. So that's another pair of action and reaction. So everything consistent. Everything is consistent, right? So this person is going to get a force, okay, from the ground, a friction force, to stop him from slipping in that direction. Okay? So that's a force from the floor on the person. Okay? So now you see that, imagine that the box is really heavy, you want to push it this way. Your feet are also going to push the ground really hard in that direction. Think about it. You can do the experiment, right? You can never push a box without pushing the ground in that direction really hard, okay? Imagine if you do this on an ice surface, you can never push anything because you're not getting any force from the ground, okay? So if you push really hard on the floor, you're getting a really large force in that direction. And then you can take a look at this person. How many forces on this person in horizontal direction? This one and this one. How does the person move? It totally depends on which one is larger, right? So in order to push this box, you're going to push the ground really hard in that direction. So you get a really large force, reaction force from the ground on you in that direction. So the net force on this person, okay, it's going to be the force from the floor on this person, right? And then minus the force from the box on the person. So if you're getting a very large force from the ground, you're still going to be moving in that direction, no question, because this guy is going to overcome the force from the box on you. Okay, so you will be moving the same direction with the box. Okay, that's how you explain this. Okay, so I hope this has clarified this confusion. Okay, a lot of people, they have some confusions on this case. Okay, they don't know the relation among all these forces. They don't know how to compare these forces. Okay, so the reason the person moves in that direction with the box, it's not because you are pushing the box harder than the box pushes back on you. No, because these two forces, their action and reaction, the force from the person on the box and the force from the box on the person, action and reaction, they are always equal. You don't need to compare them. Okay. The reason the person goes in that direction, because the person is going to get a very large force from the ground, because the person needs to push the ground really hard in that direction in order to move in this direction. Okay, so that's another pair of action and reaction. You're pushing the ground in that direction, the ground pushes you in this direction, and that force is going to overcome this force. Okay, everything is consistent. Everything is consistent, right? But you do need to do some hard thinking. Okay, once you have thought everything through, okay, everything is going to start to make sense to you. Everything. You're not going to be confused. Okay, but you always need to use the laws. You always need to consider everything. Okay, if you miss something, okay, you're not going to get the right answer. You're going to confuse yourself, right? So you should always use the laws, okay? And then you should consider everything involved. You will get the right answer, okay? So you have to do a lot of thinking, okay? Sometimes it's not that intuitive. You use the laws, you do the thinking, everything is going to start to make sense. Everything is going to be consistent, okay? All right? So then, what about the third case? Say the apple is pulling the orange in that direction, right? Okay, at the same time, the orange must push the apple in the opposite direction. How do you explain the apple is still going in that direction? If you tell me the orange is pulling this apple back, right? That's action reaction, okay? Apple pushes orange in this direction, so pulls the orange in that direction, the orange must pull apple in this direction. But again, the apple is pushing the ground really hard. It's pretty much like this person, right? The apple gets a force from the ground in this direction. That force is going to overcome the pulling force from the orange only. That's why the apple can move in this direction with the orange together. They will both moving in the same direction, even though the action and reaction forces between them are opposite, right? But if you want to figure out the motion of an object, you need to consider all the forces on it. You can't just take a look at one force and say, okay, this object must be moving in that direction because there's a force in that direction, right? That's a mistake, right? You can't say that I have gravity on me, so I have to be moving down all the time. No, right? You need to consider all the forces on you so you know how you're going to move, okay? So this is this question. Okay, now, okay, because we have learned action and reaction, okay? Sometimes people are going to confuse action and reaction forces with balance forces. Why? Because balance forces, they're also equal, right? They're also in opposite direction. That's why they're going to balance out on an object, okay? Action and reaction, we learned they're also, okay, equal object. So sometimes, once people have learned Newton's third law, they tend to confuse action and reaction with balance forces. Okay, so don't confuse them with each other. They're different. Okay, so now we're going to discuss the difference between them. What are balance forces? Okay, so for example, if I place anything on this surface, okay, so I want you to draw the Fourier diagram of this object. I want you to draw a Fourier diagram of this object. I would just do this, right? If there's a box on the surface, I would draw gravity, normal force. Okay? They are balance forces because they are on the same object, okay? and then they cancel out exactly, so this object doesn't move, or this object is moving with a constant velocity, okay? They are not called action and reaction. Why? Because they come from different things, okay? They are not the force between only two objects, right? What is this force? This is a force from the surface on the box. What is this force? This is the gravitational force, force of gravity from the Earth on the box, right? You see that this is not a paired up. It's not a action and reaction force are the two forces from A on B and B on A. They pair up. You call them action and reaction. They're going to exist at the same time. They're going to disappear at the same time. These two forces, they're not even connected. Why do they cancel out on this box? Only because I place this box on the surface, right? Say if I lift this box off the surface, do they disappear at the same time? No, right? If I lift this box, this force is going to disappear, right? But the gravity from the Earth on this object is still there. So you see that they are not action and reaction. These two forces, they are not action and reaction. They are balanced forces. It's just a coincidence they act on the box at the same time because I placed this box on the surface, right? So it's a totally coincidence, okay? There's no way I can predict these two forces. They're going to act on this box at the same time. They cancel out each other exactly, okay? They are balanced forces. They're not even connected, okay? They just happen to act on the same object and balance out each other. We call them balanced forces, okay? Actually, what is the reaction force to this force? That's going to be when you draw the force. I can draw the action and reaction for this force. The reaction force to this guy is going to be the force from the box on the Earth. That's the action, that's the reaction force to this force, right? These two guys, they are action and reaction because they are the force from the Earth on the box. At the same time, simultaneously, they are the force from the box on the Earth. But I don't draw this force on the box. I don't, because that's a force on the Earth, right? So action and reaction, they're always on different objects. They're connected, right? They're always between A and B. But these two forces, one is on A, the other one is on B. There's a symmetry. But you never draw action and reaction on the same object, right? These are action and reaction. These are action and reaction. But I don't draw both of them on the Earth. I don't draw both of them on the box either, right? I would draw them separately. This force is from the Earth on the box. I would only draw that on the box. The reaction force is from the box on the Earth. I don't need to worry about that when I draw the free body diagram of the box, okay? Because I don't need to draw the force from the box on the Earth. What is the reaction force of this guy? So that's the force if you draw the surface, like the table, right? The box is going to have a force on the table at the same time. That's the force from the box on the surface. Again, you only draw that force if you are interested in any force of the surface. Usually we are not interested in that, right? The surface is not going to move, okay? It's a fixed surface. So we usually don't draw that force. But these two forces, they are action and reaction, right? But I never draw them on the same object because they are on different objects, right? One force is on A, one force is on B. They are equal and opposite, but they are on different objects. So I never draw them on the same object. Okay, so that's the difference. Okay, these two guys, they're balanced forces. It's just a coincidence. Okay, I placed the box on the surface so that these two forces act on the box at the same time. Okay, but they are not even connected. Okay, you can predict. Okay, these two forces are going to be on this box. Okay, always. So they cancel out. And then another difference is this. Action and reaction, they're always a pair, right? Always two. If you talk about action and reaction forces between A and B, it's always going to be two. Balance forces don't have to be two, right? Say if I push this guy really hard, okay? Damn. How many forces on this box now? You would redraw the Hilbert diagram, right? So you would have 3 forces on the box, right? So I would draw this. The box has gravity down. I'm also pushing this force down. And then, of course, the normal force on it is going to get larger so that all these 3 forces now, they're going to balance out. So now, these 3 forces, you would call them balance forces, okay? Why are they balanced? Well, only because I place this box on this table, I'm pushing this box down. That's why, okay? It's just coincidence that these 3 forces are acting on this box, okay, at this time, so these 3 forces are balanced out. They're not connected, right? There's no way you can predict it, that these 3 forces are always going to cancel out on a box. No, right? But in this case, these 3 forces, I call them balance forces. They don't have to be 2, right? They're not action-reaction. They have nothing to do with each other, right? Okay? So balance forces can be, 2, 3, 5, right? Whatever, like how many forces on this guy. If this guy is at rest or moving at a constant velocity, it's always going to be balance forces. You call all these forces as balance forces, okay? All right? So that's different. That's another difference between action and reaction and balance forces, okay? Okay, I know that a lot of people, they will feel confused, okay, because these 2 things, they're very similar, okay, action and reaction. Let me use an everyday metaphor to help you understand the difference. Take a look at the next slide. Consider that Newton transfers $200 to his bank account to his girlfriend because his girlfriend wants to buy a nice dress, okay? So, well, this is probably not true because Newton never had a girlfriend, okay? But anyway, let's use this to help us understand the difference between action and reaction and balance forces. So you can consider these 2 transactions, action and reaction. If you look at Newton's account, you will see a transaction negative $200, right, showing up on Newton's account. And then if you check his girlfriend's account, you're going to see what? You're going to see plus $200 as a transaction. These 2 transactions, they occur in pairs simultaneously. It may take the banks to update their transactions, but theoretically, these 2 transactions, they occur in pairs simultaneously. They are the reason of each other. The reason his girlfriend gets this transaction positive $200 in her account is only because Newton has this negative $200 on his account. He transfers this $200 to his girlfriend. So these 2 transactions, you can consider them as action and reaction. You see that you only see one of them in one person's account. You only see negative $200 transaction on Newton's account. You only see positive $200 on his girlfriend's account. You never see both of them on the same account. You don't, right? So you shouldn't say that these 2 transactions cancel. So there's no change in either Newton's account or his girlfriend's account. No, right? There's definitely some change in Newton's account. He lost $200. He's not going to be happy, okay? His girlfriend got $200, and she's very happy, okay? These 2 transactions, they don't cancel, right? They are action and reaction. You should never say they cancel, because they don't, right? There is some effect in Newton's account. There's some effect in his girlfriend's account, okay? Now consider the next slide. So, okay, Newton transfers $200 to his girlfriend. The second day, Newton received a refund, $50 from Amazon, okay, for an order he returned. Okay, good. So you're going to see another transaction, plus $50 on Newton's account. And then the third day, say Newton gets a check, $150, okay? And then Newton deposits this check to his account. So if you check Newton's account, you're gonna see another transaction plus $150. So all these three transactions, they happen in Newton's account. If you add these three transactions together, you get a zero, right? So if you remove these three transactions from Newton's account, you're not gonna see any difference, right? So these three transactions, they cancel out, you can say, in Newton's account. So there's no change in Newton's account, the balance in Newton's account. But these three transactions, is there any connection between them, right? Did Amazon refund Newton because they knew that Newton transferred $200 to his girlfriend? No. Did the person who gave Newton this check knew that Newton transferred $200 to his girlfriend so that the person gave Newton a check? No. These three transactions, they're not even connected. They have nothing to do with each other. It's just a coincidence that they happen in Newton's account on 3 days, consecutive 3 days, so that they cancel out. You add them together, it's just a lucky coincidence. You got a zero, and then you can totally remove these three transactions. There's no change in Newton's balance, right? So you can call these three guys balance forces. They're like balance forces, right? It's totally coincidence. They happen, they act on the same object. You add them together, you get a zero. So this object either is at rest or moving at a constant velocity, right? They are not action and reaction because they have nothing to do with each other, okay? You remove one, the other one still exists, okay? So that's the difference between action and reaction. So I hope that everyday metaphor helps you understand the difference between these two different scenarios. Action reaction is different than balance forces, okay? So I'm going to stop here for this video.